Okay, Assalamualaikum and good afternoon. So welcome back after a week, a good weekend hopefully. Uh, so let us recall what we did in the past lecture. So let me go to my notes. Okay, recall what we did was to look at powers of complex numbers. Can you hear me all right? Anyone? Okay. Okay. So I think I mumbled something at the end of the lecture, which I can't remember. I have not seen the recording myself. There was a bit of a fumbling about this picture. Let me recall what's the problem is all about. Essentially, you remember when we go from Z, is it not working? Okay, there's a bit of delay on my tab. Hang on for a while. Just want to check. My tab seems to be pointing all right, but there it is. Okay. Remember when we do conjugation, what we did is essentially we talked about say Z over here, okay, and then essentially Z bar or Z star is actually a reflection about the what we call this x-axis, which is the axis of y equals to 0. So y equals 0 means this is your x-axis. Okay. So really is the reflection about the y equals 0. In that case, you'll find that, okay, this gets reflected to that. Now, I also mentioned that when you solve for these roots of powers, you're supposed to get pairs, right? So if this is a root, then another readily available root will be just the conjugate. And it doesn't seem to be happening here, but it is there. Instead of taking y equals 0 in this particular case, so if you look, this would be the rotated y-axis. So this would be the new axis for which one should see the reflection. So then you can actually see, is that right? Let me just confirm that. So that maybe not that axis. So which axis is it? So this gets reflected there. So I have to find the right axis. But in other words, you can actually see things coming in pairs. I just want to see where precisely the axis is. So this will be the angle here. And that will be that. So this will be the pair. So no, that cannot be. That, what will be the axis? The axis will be here. So in other words, essentially, okay, I'm just trying to do this by, spontaneously. I might not get the right one, but essentially, it's just your complex plane has been rotated in a way, so you don't actually see precisely the reflection that you're supposed to see. Okay, but if you figured out properly. No, I have not figured out at this particular point in time, but you can actually find the axis over which there is a reflection for all the roots. Okay, so I will not try to fumble again. So, but maybe I will try to do this as a quiz later on or something. Okay. Okay, so let me proceed today with a new topic. You might be seeing a delay a bit, yeah. Okay, we'll look at the case of complex functions rather than just complex numbers. Okay, so one of the things that we would like to do is to talk about power series. Okay, so in the past you have seen power series in the variable of x or something or theta, where your variable is real, but now we would like to see the case where it is actually a complex number. Okay, so one of the things one could actually try to generalize is the idea of your series, instead of just having if it's in the case of the ordinary function that you talk about, the power series, for example, then your series will be just in the form of powers of a real variable. Okay, but now one extend this simply to the point of splitting the variable into two parts. Okay, so in other words, your variable is now z, but you can split it into this Cartesian form, and then when you do powers over this, okay, so you have z to the n, so you know how to do powers now. It's a bit delayed. Then you could essentially expand this if you want to. You do not need to do this by hand. There are things like Wolfram that can actually do this for you. You've seen it in the case the previous lecture thing. So in other words, you have this power series. So this will be broken into two parts. Okay, in that form. Okay, so in other words, this is not quite as transparent in the case of the power series of your real variable. Okay, but definitely you have something here that depends on z and something here that depends on z. Okay, so in other words, one could actually try to do in this particular case, you have real parts for the function and the imaginary part for the function. So in other words, let's have f of z, then there will be a real part of f of z as an imaginary part of f of z. Okay, so in other words, we have, if it's a power series, then you have all these terms coming in, okay, into this. So in other words, what we need to think about is this series with real and imaginary components, and you can do a partial sum of each of those components. Okay, the real components will have a partial sum and the imaginary components will have a partial sum. Okay, so one could have something like this. So you have this partial sum about the real part, which is I call it capital Xn, and the imaginary part, which I call as y, capital Yn, and both Yn are real in that sense. It's just that so this is all real, involving a real function, so to speak. Okay, and one of the things that we would like to worry about is whether this sum that you broken into two parts over here, so a necessary thing to have, if it has a limit in this particular form, okay, this would be a limit, so you have the real part and imaginary part, then you would like this partial sum or this series, okay, would also have its individual limits. Okay. So these are things that we need to worry about, but most of the time we will only work on functions which have proper limits. Okay, so but again, now we have something extra to do. Okay, because of this two series that seems to appear on both parts of the real components and the imaginary components. So one of the things that we need to worry whether is it convergent or not. So one could go through some examples over here. So here is a series. Where's my cursor? Can you see my cursor moving around? Somebody please confirm. Okay, okay, good. So so you can see this series, which is now a series of complex numbers. So you can think of what would be the, so it's like I okay, that would be a complicated thing. Okay, now I wouldn't want to do this. So what one needs to do is essentially to have say for example no explicitly write those series down. Okay, so in other words, the first term will be the case of here. No, we start with n equals to 1, so then it will be I to the power 1 square root 1. So that's why we do not start from 0 there, because we have a denominator will be 0 in this particular case, and that just blows up. So you have I to be the first term, and then you can start doing the second term, third term, fourth term, fifth term, and then you can see that imaginary part here, and then you have the real part, imaginary, real, imaginary, real. So if you want, you can break it up in those forms. Okay, so in this case, we have seen the real part is that. Okay, so you get that is the first term, sorry, for the real part, and then the imaginary part, you have to remember, the imaginary part is without the I. Okay, so in this case, what multiplies I over here is 1. What multiplies I over here is minus 1 on root 3. What multiplies I here is 1 on root 5, and so on and so forth. So in other words, here you have the real part to have this particular series, and then this part will be for the series of the imaginary part. So one asks the question again, is it convergent or not? So let's see. We go down. So if you look at that, you can remember we had a few tests to see whether a series is convergent or not. So in this particular case, if you look at the signs here, where is my cursor? Okay, if you look at the sign here, they are alternating. Okay, so then you can actually, okay, since the sign is alternating, then I will look for those tests which is used for alternating series tests. I can't remember what precisely it is, but you can look at the lecture 1, I think, if I'm not mistaken. Okay, so and you test those for this real part and imaginary part, then both are actually convergent. So that means this is convergent and this is convergent. Okay, so you check the convergence of the series, of this particular series. Okay, so in other words, if the real part is convergent and imaginary part is convergent, then we say the original series in terms of the complex numbers is also convergent. Okay, so the next thing is to do another different example for which you might not have. So in other words, the first example seems to have it. It's convergent for all um, real and imaginary parts. Okay. Now we look at this particular case for which it is the series is actually in terms of power series of no the powers are actually in terms of complex numbers. Okay. Previously it was just simply an I over here. Here you have both. I seem to have a delay with my pad. Here you have both real and imaginary in the powers. So this is a bit more complicated. So again, what one needs to do in this is to look at one of the things that we learn easy to test is the idea of ratio test. Okay, so you take the term, say an plus 1, divide by the term an, and to see whether is this less than 1 or greater than 1. Less than 1 means it's convergent, and greater than 1 is divergent. Equals to 1, then you have to do other tests as well. Okay, so one could do that. But now, because this is complex, one should be looking at the absolute value. One looks in terms of this. Okay, so if you look at this in this particular case, then you'll see that the n plus 1 term, okay, the n plus 1 term is actually having that, and this is the n term, so your powers essentially cancel off, so you get 1 plus I on top, and then on the denominator you have just simply 2, and then you take the absolute value, and plus I would have square root 2. Okay, it's just that 1 squared plus 1 squared, okay, square root 2, and the absolute value of 2 is just simply 2. So you get square root 2, which is a number less than 2. So in other words, this is going to be less than 1. So in other words, this series by this ratio test would be absolutely convergent. Okay. Okay, now we come to the tough part. Okay, previously our complex series, power series, is given by a specific z. Okay, that means z equals to, in this particular case, z equals to 1 plus I. The previous one is z equals to I over something. Okay. Okay. So now we consider this in general, where z is now a variable. Okay. So and the other thing is, okay, z is complex to the power of n, okay, meaning it's power series of a complex variable, and then you have the coefficients over here. Delay again. Coefficients over here, then you'll find that coefficient is generally a complex number. Okay. So now this is a bit more complicated than before, so one should try to see some examples first, and then how this would actually generalize from the previous version. Okay, so here is a example over here given by 1 minus z to the power 1 divided by 1 plus z over 2 divided by 2, so it's alternating. Okay, but that alternating is actually involving z, so alternating power series test will not be so helpful over here, but you have the absolute condition if you want. Then one looks at the n plus 1 term again. So the n plus 1 term will be the n plus 1 term. So let's look at the n term first. N term will be, I would need minus 1 to the n, right? Zn divided by n. And then n plus 1 term will be minus 1 n plus 1 Zn plus 1 divided by n plus 1. Okay? So one can divide these two terms together now. So your minus 1 to the n, minus 1 to the n plus 1 is going to be divided by minus 1 to the n. Zn plus 1 will be divided by z to the n. And then n, which is actually appearing at the denominator, and then appearing at the denominator will become the numerator, and that is going to be divided by n plus 1. So in the end you have this ratio. Okay, and you take the absolute value of that, and that seems to be giving you that will give you modulus z n over n plus 1. But as n goes to infinity, so now we look at the limiting case. So limiting of n goes to infinity of n over n plus 1 is just going to be equals to 1. But you still have this part, which is limiting of n goes to infinity. So I'm breaking into two parts now really. Z is just simply z. It doesn't give you any particular value here because z is a variable. Okay, so in other words, what one needs in this particular case, if this is going to be a convergent series, then it will depend on this value of z. Okay, if this value of z is, if this absolute value of z is less than 1, then essentially it's going to be convergent. But if this absolute value of z is greater than 1, so in other words, in this particular case, when you talk about this series, we have the idea of a radius of convergence. Okay, so in other words, what we need in this particular case is that for convergence we need modulus z less than 1, and if you plot that, if you plot this locus or those numbers that represent this condition, so I can draw a circle first. So this would be the circle of z equals 1, modulus z equals to 1, and modulus z less than 1 will be the disk. So in other words, over here we have what we call the disk of convergence. So any complex number inside this disk, anywhere, will give you a convergent series. Outside it will give you a divergent series. And of course, the border of this disk, you probably need more tests to do this. Okay. So anything that lies on the circle there, you probably need to test it in more detail. Okay. But the idea is now you have this disk of convergence with radius 1. So that means this is r equals to 1 here. Okay. So then you see that, okay, our power series in the complex numbers will depend on precisely a particular region of the complex plane. Okay. So in this particular case, it will depend on this disk of radius 1. Could be displaced, this disk is going to be displaced, and so on and so forth. Okay. So, okay, I think that one example could be sufficient to look at the case of this radius of convergence. You might want to see some other case here where your of convergence is actually infinite. Okay, so this we consider this particular series. Okay, and then you can see that, okay, what's the term, what's the n term here? The n term would be I z to the n divided by n factorial. And what's the n plus 1 term? Will be I z n plus 1 divided by n plus 1 factorial. So you take the ratio of these two terms, is this divided by that. So then you actually get this. Okay, and remember that since this is a complex number, you need to take the absolute value. So in this particular case, if you take the absolute value and take the limit n goes to infinity, so you have some number. Okay, remember that absolute value of I z n plus 1 as absolute value of I z divided by n plus 1. Okay, and this is, no, your I has absolute value 1, so this is just simply, okay. So now that we have that, so and if you take the limit n goes to infinity, so you have an infinity at the bottom, and that gives you a 0. So in other words, your radius of convergence in this particular case is actually infinity. And that means whatever z value there is, okay, that series is convergence. So you have, you can think of your d's previously, your d's are now, okay, goes to infinity. So you have a d's at infinity. Doesn't seem to come out. Okay, there's a delay here. So that your d's has infinite radius. So in other words, whatever the values on the complex plane, okay, this series is going to be converged. And we are mostly interested with this type of power series, and these are sometimes called in complex analysis. We are not doing complex analysis here, not at this first part of the course. This is sometimes called an entire function. That means the power series is convergence for the whole complex plane. Okay, so we are mostly interested in those kind of functions when we do, at least at this point. Okay, so we should know, however, how to find the radius of convergence and this of convergence. Okay, so that we leave it to your exercises in the book for you to play around with. Okay. Any questions at this point? You have this particular loaded, the next one though. Okay. So probably we just continue. If there is a question, please shout, because I can't see you. If you do a message, I will not be able to see it also. Okay, so you just need to voice out. Right. So now if you look back at the function that we are, this example, what I call it example 4.4, in this particular case, this is just something that you have seen before. This series is something like 1 plus x squared over 2 factorial plus x cubed over 3 factorial, where your x are real in this particular case, then this is just exponential x, right? So in other words, over here, this is really what? This is exponential iz. So we have demonstrated a function now of a complex number, or in this case a complex variable, which is a convergent function, I mean in all values of z. Okay, so you already have seen one example of the exponential function of a complex variable. Okay, and in this particular case, one should be easily, no, this is the one that we look at the example. One could actually see that if this is convergent for the whole complex plane, then one would expect exponential z is also convergent for the whole complex plane. And if you really see what it is, okay, if you really see what it is, then I could write your e to the power z to be e to the power x plus iy, okay, but I can factor that exponent into two parts, which is exponential x and then exponential iy. And this is a convergent, your exponential is a convergent for real variable, but you also have seen that this one is simply cos y plus I sin y. Okay? So no matter what z value that you take, this is well defined and this is well defined. So in other words, exponential z is an entire function for which you can take any value of z for that matter, and you still have a well-defined function with whatever the value of x and y is supposed to be. And I'm having problem with my tab. Okay. So here's some easy examples for you to check. So here is x plus I 16 pi, and that becomes exponential x, exponential 3 plus I 3 pi. So you can check that, okay, remember that exponential I pi is always minus 1. And then that means exponential I 2n plus 1, again 2n plus 1 t, okay, and that equals to minus 1. Okay, these are good things to memorize. This is equals to 1. Okay, so you can start checking all these values, and then you will see that everything is well defined. So, okay, this these are just a reminder of what we had earlier. Your sine theta can be written in terms of this, and cos theta is written in terms of that. Okay, but here essentially your theta is a real variable. Have I actually introduced this before? I can't remember now. I know I introduced it in terms of powers. Okay, so this one will have odd powers and this one will have even powers. Anyone? Okay, maybe not. So if you remember, EI theta gives you what? It's all all powers are there. So yeah, I theta n factorial, and then e minus I theta is, okay, then I will have this minus 1 to the n theta to the n over n factorial. So if I add these two things up, okay, then I will have problems. Well, not really problems. If I look at what is, when n is odd, I will have an extra minus sign, right? If n is even, that's fine. So that means when you take ei theta plus e minus I theta, then what we have is we get this series, the odd powers cancels off from both series, and you're left with this even n. Okay, and similarly, if you so that gives you a cos theta there, and then if you do the difference between the two, then you get instead of even powers, then you get an odd powers. Okay, so you get back to the same notion of your sine theta expanded in terms of odd powers of theta, and your cos theta will be expanded in terms of even powers of theta with alternating sign. That's another thing that I should mention. Okay, so now what we want to do is, okay, we know all this previously from the power series with real variables before that, but now what we want to ask, can we do this for, say, complex numbers? Theta is real, but now suppose I want to do sine z, where z is actually a complex number instead. Well, we can just simply adopt the formula that we have over here. Okay, your sine z is given by that, and your cos z is given by that. So it's the same, it's almost the same formula, but it's understood differently now, where your theta is real, here z is complex. And one can check a few, and these are fine. These are all, you remember that exponential of I of z is a convergence series, exponential minus I of z is also a convergence series. So there's no problem of defining these two. Okay, so what one could try to see is how to evaluate this. Okay, so here again are some examples just like before. We look at certain values of z. So let's see, if I take z equals to I, what does it mean by that? So it's just plugging I into z in the formula. For example, over here is exponential I times I, and then over here it will be exponential minus I times I, and here is I squared, that gives you minus 1. Here is minus I times I gives you a 1. Okay, so that's easy enough for us to do. And one thing that, okay, the other thing that you have this 2i at the bottom here, one could remove the complex, remove the imaginary, what you call, remove the imaginary nature of the denominator by multiplying with the conjugate of this. So you multiply minus minus I top and bottom. So here is also minus I. 2i times minus I gives you a 2, and then you have a minus I here. Your minus flips these two ordering, so it becomes e to the power 1 minus e minus 1, okay, times I. Okay, and if you evaluate this, this is just simply that number. Fine. Okay, let's do a slightly more complicated thing. Okay, what about, okay, I log 2? The reason here we use log is why, again, sometimes in writing down the examples, sometimes you need to try to use a particular value that allows you to evaluate this easily, because exponential, okay, has the inverse mapping of it is a log. I think you have seen this before. This is actually equals to x. And log ex is x. So they are sort of the exponential is the inverse mapping will be a log, and the inverse mapping will be an exponential. Okay. So that's why I'm using this log there, because I know I'm going to plug this thing into your exponential. So I get what? I exponential I times I log 2, and then exponential minus I times I log 2, and that gives you exponential minus log 2 and exponential log 2. Now exponential log 2 is equals to 2, okay, which is that. Okay, exponential minus log 2 is really what? It's exponential log 2, come on, lagging again, log 2 power minus 1. Okay, and then you this is equals to, if you know the properties of log, this will bring the minus 1 up here, and you get back your minus log. So, and this again is just like before, log of x. So this is log of what is 2 minus 1 is simply equals to half. So this will be just a half. Okay, so you need all please get all your knowledge of functions like this, so that you can evaluate these things easily. So now I can evaluate the whole thing now that it becomes 504. Okay, so it's well, so there are, I suppose one could give you a lot more examples, but no, I think you probably get the idea now. Okay, of course, in most particular case, if you have a horrible z there, then evaluating this will take a little bit more process, but essentially whatever the complex number that you input here, you can always have a particular value. Okay. All right. One other thing that we also know about, so in other words, all this cosine z, sine z as a complex function are well defined, but one of the things that we know about cosine and sine previously, if it's a real function, we know that this works, right? This is always true for any real variable x. So now we need to show that, okay, will this be true for the case of the complex variable? So we need to prove that. Okay, well, it's easy for us to do that because where is sine squared z? Sine squared z is just this function of the exponential there, square them, and you get that. Okay, and then move this forward. Okay, cosine squared is just that, squared, and then you have that, and then you add them together, and you can see that, okay, let me see, over here, okay, I've forgotten, here you have 2i, and you have to square that as well, so that gives you a minus 4. So in other words, this is really what? This is minus exponential I to z plus 2 minus exponential minus I to z divided by 4. Okay, and then you add this up, you can see this one, for example, will cancel off with that. This one will cancel off with that. The one that's not been cancelled is this 2, okay, which is now positive because of the minus sign there. 2 and this 2. So you add the numerators, the remaining numerators there. So you get 2 plus 2, which is 4, and 4 over 4 is just equals to 1. Okay, so in other words, we can do all this. You can try to identities for your trigonometric function that you know in the case of the real variable, and you can try to see whether that also holds in the case of the complex variable. Try those. Maybe you can try, say, see whether that double angle, okay, I have not checked this myself, but check if the double angle formula is still true. Okay, so there are plenty of things for you to play around with to see. Okay, maybe it will fail somewhere. Usually not, but no, that means your cosine and sine function, if it's true in the real sense, it's also true in the complex sense. Okay, here's another thing that you already know, now involving a little bit of calculus here. So you know that, for example, d theta of sine theta is cos theta, and another one that you know is d theta of cos theta is minus sine theta, right? Now theta is a real variable in this particular case. Now we would really want to consider the case of, say, if it's a complex variable. Here I leave it as an exercise again, just like this one as an exercise. Okay, so you can actually try to do that at home. But the idea is, whatever properties that you have for the trigonometric functions in the real case will also hold in the complex case. Okay, so that is manipulation with your sine and cos. But you have other trigonometric functions that we had seen before. Your tangent, you can define that. Since sine is well defined for z, cos is well defined for z, then tangent is also well defined for z. Same for our secant function, cosecant function, and so on and so forth. Let's see how much more. This is page 5. Okay, let me just continue with this hyperbolic function, and then we'll take a break, say around 3 to 5 minutes. Okay, so we consider now our hyperbolic function, which is related to your trigonometric functions. In what sense? If you do ei theta plus e minus I theta over 2, then this gives you cos theta. But if you do with the instead of I there, you replace it by x, then you have a what you call a hyperbolic cosine, or I just call it cos, and then you also it avoids me to see hyperbolic every time. Okay, cos and sine. Okay, so since your exponential is already well defined for z, any complex z, then one could imagine that this is also true for the case of the hyperbolic functions. So there's no worry about that. So you can always define those. Okay. So once you define your hyperbolic functions there, you can also get the other functions that that you have seen before, like hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, and hyperbolic cosecant. And you can and one of the things that one should try to do is also prove the identities. For example, in the case of the real variable, you have that instead of your cos squared plus sine squared. So you have this equals to 1. You can also check that this is true now for the case of z, okay, the complex variable. And again, if you're doing calculus, you know how hyperbolic cosine under the differentiation, it gives you the hyperbolic sine. This is also true. So again, this is just no, all these exercises are just simple exercises where you just plug in your expression for the cos z and sin z. Okay. Okay, maybe I'll take a break now. So let's take a break for about 3 to 5 minutes. Okay. Is that okay, or do you want to carry on? No answer, I carry on. Okay. Okay. All right. Okay. We'll take a break, say about 5 or less than 5. Okay. Is everyone back? Okay, great. Okay, let's continue. Okay. One of expanding your cosine or the trigonometric functions and the hyperbolic functions also allows you to see the relationship between the two between the trigonometric functions and the hyperbolic functions. For instance, now I can just think of a cosine with just a pure imaginary function there, pure imaginary variable. So I can see that this, when you plug into the formula, I'll get your real exponential there, and this become a hyperbolic cosine. Okay, and similarly, if I do this for the case of the sine function, then this almost related to the hyperbolic sine, but now you have an extra I factor there. Okay, so you can see the relationship there. Cos iy gives you hyperbolic cos y, sine iy gives you I hyperbolic sine y. And similarly, you can do it for the case of the hyperbolic function also. Hyperbolic cos iy gives you something cos y, and hyperbolic sine y gives you imaginary I times sine y. So these are nice things to remember in a way. Relationship between trigonometric and hyperbolic functions. Okay, so I think we have enough of this. At this point, we want to go to something else. Okay, so one of the things that we have seen earlier about powers of complex numbers, and with powers of complex numbers, the inverse mapping of powers are actually the logarithms. Okay, so we can also start to think of, okay, let's consider those as complex functions and see how this plays out. Okay, so as I said, exponential function, the inverse function would be a natural log, so your ln. Okay, so now we try to extend this to the complex variable. Suppose I have z equals to exponential w, where both z and w are complex. Okay, then this relationship between the exponential and log will also hold in this particular case. So you can see over here, then w will be the log of z. Okay, so in other words, you can almost see that if I do exponential w, then this is exponential log of z, and that's the inverse of each other. Okay, so that gives you that thing back. And if I put w equals to log of e, log of w is log of EW. Okay, now how does this plays out? This is essentially well, okay, we take the fact that this is now a power, so I can write this in this way. W, oops, z, this I can write, since I know the behavior of the log is this w log e, and log e is simply equals to 1. Okay, okay, now we can check for other properties as well. Say you multiply two exponents, for example, and you get w1 plus w2. So if I take the log of this equation, so I get log of z1 plus z2, then I would actually take the log of this exponential, okay, and then that will play out, since log and exponential are inverse mappings or inverse functions of each other, then this becomes w1 plus w2, and this is, if you remember, w1 is log z1. For example, I didn't actually write that down, but never mind. w1 is log z1 and w2 is log z2. So now you have two things. One is this inverse of this thing, okay, but the other one is, now we also verify the fact that the log under a product gives you this additive property, which is great. All the things that you know for the log function also holds in the case of the complex numbers. Okay. Now, let's try to understand. I mean, log is not as okay. For that matter, the complex function is not as transparent as a real function, because you know, one of the things that one needs to do, then you have to really break it up into two parts, and then you find that, okay, you have how the real part of the function behaves and how the imaginary part of the functions behaves. This is also true for the case of the trigonometric. Okay, so it's not so if you have sine x plus iy, for example, you could actually try to, so this is z, okay, remember, so one could actually see that, okay, one can apply the addition formula for this, and then you get something else, which is what, sine this is what, sine x cos iy plus cos x sine iy. And then you have seen cos, what is cos iy, sine iy, and then you can turn it to the hyperbolic function. Okay, so it's not as transparent as the one with, say, with the case of your real variables, but no, again you can see that all this expression that we have here are all well defined. Okay, Now, the case of the log is a bit because the log tends to have this what we call multi-valued kind of property. Okay? So what is, say, like the previous one is the log of z, what was it? Yeah, log of z, and what one can actually try to do, rewrite your z instead of x plus iy, you can write it as rei theta. Okay, that's interesting because why? When you take the log of this, I have this log property together with the exponential thing. The only problem with that, so one could just simply write then, okay, I get this log r plus log exponential I theta, but that doesn't give you the whole picture of the of this particular part. Okay, because you have to remember, like the case of the powers and roots, when you take the roots, you have to remember that you can break up into more roots when you have the complex behavior. So what one needs to do is to think of this as exponential I theta times 1. And what is a 1? 1 is given by exponential I to n pi, where this n can run from 0 until infinity or minus 1 until minus infinity. Okay, so one has to look at those properties, and if you do that, then this doesn't just give you I theta, but it gives you this I theta plus 2n pi. Okay, it's a multi-valued property. Okay, because there will be different values of theta possible. What about the other one is log r? Okay, well, I mean, initially it was like that, and then I put this capital Ln because over here everything is actually real. Okay, so this is a real, the logarithmic function over here is a real function. So I'm just making the difference between this log, which applies to a complex case, and then when you put in this polar form, this is actually the real log function. Okay, just to differentiate between the two. So then you have this real part, and then the imaginary part is given by these angles that you're supposed to have. Okay, so you have this multi-valued property that makes it a bit well, it depends on the kind of problem that you want to solve, but as a function is well behaved if it has one particular value for one particular variable. Okay, so z is one particular variable, but here it seems to give you all these different values of theta. So normally what people do is to limit this multi-valued property to a particular branch, because here it goes to you think of what happens over here. I'm taking theta over here, and then I repeat the whole thing again. I get another branch, so again, and then another branch, but it all gives you the same point on the complex plane in some sense. Okay, so we want to limit this to a single value rather than multiple value. Then we either use these values of theta or these values of theta, and this we call it as the principle of log z, in order for log z over here to be well defined. Okay, and the branch of theta that we take is called the principal branch. Okay. There are uses of this. No, there are other branches, meaning for this log function, but in our no part of this course, we are not going to use those. Okay. So now for this log z, then one can actually write z is simply log of the absolute value of z plus I theta if you limit it to the principal branch. If you don't limit it to the principal branch, then you have multiple values like this. Okay. So one can now start. Okay, since now if you do this limitation to the principal branch, one can have properly defined log function for the complex variable. So one can actually check, for example, log plus or minus 1. Well, if I just do, okay, in the real log function, log 1, or I should write capital log 1 here, which is limited to the real variable, then this is actually 0, right? But if I consider 1 to be in the complex, the set of complex numbers, then I should be thinking of I to n pi, for example. Okay, or in the case of the principal branch, it would be either, okay, this is for the multiple branch. For the principal branch, I should take I to pi or e plus or minus I pi. So there are two values, e to 0 and e I to pi. Okay. So now what happens in that particular case, log 1 is actually the real log 1 plus or minus I pi. So it gets extended to have an imaginary value. Okay. Of course, log 1 here is 0, of course. But now what happens also, we could extend this to log minus 1. Now in the real log function, log minus 1 doesn't make sense. As real function. But as complex function, no, you have that. So in other words, over here, what will happen is it just picks out the imaginary part to be either I pi or minus I pi. So in other words, your log can be extended the definition when you go to the complex numbers. Okay, and of course, if you do this with a complex number itself, then you can use the same idea again. So here, how can I define I or minus I? I can write it in terms of ei pi over 2 if I limit it to the principal branch, or minus I would be e minus I pi over 2. Okay, and I'll get back this, what you call these values. Okay. Okay, your log, as I mentioned, is related to the power function. And the natural log, for example, is the power of the exponent. Okay, but you can actually extend this to any powers, for that matter. Okay, so in this case, we're going to see that happening over here. So I can now think of, okay, a complex number to some power of complex number. Okay. In order this to be related to what we have discussed before, I can rewrite this as that. Exponential w log z is really what? Is exponential log of z to the w, okay, and this will be just z to the w. Okay, so now one could use this property of log that you already defined before to define power functions with complex numbers. Not only you have your complex number over here, this one is also a complex number. So go down. Okay, it's I to the power of minus 3i. So one of the things that we need to do is try to bring it to this form. So what is z in this particular case? Z is actually I here. So I need log z, so I need a log I here. And then your powers there becomes the multiplicative factor there, minus 3i log I. But now I know how to find log I. So log I generally will have multiple values, so I can write this one first, okay, and I'll get that multiple values, and then multiplying I throughout, okay, 3i times I gives a minus 3, sorry, minus 3i times I gives you a plus 3 pi, and then I have your I 3i multiplying 2n pi, so that gives you that. So again, over here, if you don't limit your log to a principal branch, you get multiple values. And what's more, you can see over here what's happening. You can have a real value at certain values. Oh, sorry, these are all real, sorry. So here is the case with all real values, but no, different values. Okay. Okay. So the observation, as I mentioned just now, there can be infinite values of these powers, and they are all real. I think this is the coincidence between taking imaginary here and also the imaginary part here. Okay. The other thing that one should be observing is that when you use all this log and exponential, okay, one should be understanding them. Sorry for the noise, I'm somewhere near the streets. Okay, the importance here is to use the radian units rather than the degrees. If you use degrees, then you get wrong values. Let's do another one, a simpler one than the one before. Just do I to the half. Well, again, what's the z here? So the z here becomes log z there, and the half multiplies the log z there. Then I will have log I to consider. Then log I is given in terms of these multiple values there. And then this is a nice thing that happens over here. If you multiply out, this is just exponential I pi over 4, and then this one, because of the 2n pi, could be a plus or minus, so you have these two possibilities. But I and pi, okay, I pi is what is that? Cos pi plus I sine pi, that's a plus 1, and exponent minus I pi is a minus 1. So you get two values. Well, this is good, and in fact that